Welcome to our second session on activated sludge processes. This particular session is going to talk about nutrient removal, which is something in addition to what we've talked about in the previous session on activated sludge. Again, this is not designed to teach you how to design an activated sludge system for nutrient removal. It's more of an overview to give you familiarity with the concepts and some of the designs and the way they're put together. My name is Russ Wright. I am the Chief Engineer of Westech Engineering in the Municipal Products Division. I've been with Westech for 31 years in a variety of positions. My engineering degree is from the University of Utah. I have a master's degree in civil engineering and with an emphasis in environmental engineering, and happy to have you with us today. I want to acknowledge, before we go any further, Paul Krauth of the Division of Water Quality in Utah. Some of the content in this series is from him, particularly the animations that you'll see later on in the presentation. We will talk about what nutrients are in the context of wastewater treatment and why we want to remove them. And then we'll specifically talk about the two major nutrients, nitrogen and how we remove that from wastewater, and phosphorus and how we can get that out of the wastewater. So first of all, what are nutrients? To you and me, nutrients are things like the vitamin pill that we take, nitrogen, that has zinc and all of those things in it. In terms of wastewater, we're only concerned with two, nitrogen and phosphorus, because those are nutrients for plants, and they affect plant growth, particularly algae growth, in water. So, as I said, nitrogen, and that comes in several forms. We have organic nitrogen, which basically just means the nitrogen that's bound up in the organic material in the waste. And most of that in wastewater is from urea or urine. But we also have ammonia. Just like your ammonia bleach, you take a whiff of that, it's a strong odor, and it's also a strong caustic and can cause problems in the environment. And then finally we have in the form of nitrate, which is not so harmful, but nitrate is the actual nutrient that you see in fertilizer. Phosphorus is the other one that we see in fertilizer. And again, we have phosphorus bound up in the organic matter in the wastewater, but we also have phosphorus that's dissolved in the water in polyphosphate and orthophosphate forms, doesn't really matter which one. Those are from detergents and things like that. Why do we want to remove them? Well, I talked about ammonia. Ammonia has a couple of problems in wastewater. First of all, it exerts a biochemical oxygen demand on water. If you saw our first session, I explained biochemical oxygen demand, which is a measurement of the amount of oxygen that it takes for microorganisms to biologically break down organic material. And usually when we measure BOD, we're talking about carbonaceous BOD, which is the 5-day BOD test that we normally run, where the microorganisms break down the organic material into carbon dioxide and ammonia. But the ammonia itself has an oxygen demand as well, because it can be biologically broken down, and that consumes oxygen from the wastewater also, and in some areas that's a problem. Ammonia itself is toxic to many fish at very low concentrations, 0.2 milligrams per liter, and so particularly in certain fishery waters, we need to be very careful about the ammonia concentrations. And finally, nitrates and phosphates act as fertilizer. If you pull your fertilizer bag at home out, you're going to have nitrate and phosphate as the two main components to make your grass grow. Well, unfortunately, it also makes algae grow, and that can lead to what we call eutrophication, or something that looks like this. I found this on the internet. This is about the worst example of eutrophication I could find. I don't know who this guy is or what he's doing out in there. I wouldn't go out in there personally. Now, algae is not harmful, but he's going to be green all over when he comes out. The problem with it is, although it's not harmful to you and me, it is harmful to the aquatic life in the lake. The algae blocks the sunlight, so the sunlight can't penetrate, so virtually all other types of plant growth are cut off. The algae dies in its natural life cycle, settles to the bottom, rots, consumes dissolved oxygen, so the oxygen levels may be low in the lake, at least in the daytime. I mean, in the nighttime. In the daytime, algae actually produces oxygen. Like any plant, it absorbs CO2 and releases oxygen. But it makes the water very murky, and about the only things that will live in there are carp and catfish. So it can really change and damage an existing ecosystem. Nutrients are receiving a great deal of attention now in the United States and internationally, and we're recognizing the need to remove them from wastewater so that this type of situation doesn't occur. Leading right into that, the US EPA federal standards for nutrients in a wastewater treatment plant effluent, there aren't any. There is no federal standard. That surprises some people. However, coming soon to a theater near you, the EPA is under a great deal of pressure to enact nutrient regulations. They have in turn put pressure on the states individually to come up with their own nutrient limits that make sense in their particular states for their climate, et cetera. And several US states have now adopted nutrient regulations. I live in Utah, and just about 6 months ago, the state of Utah passed a phosphorus regulation for the first time. And so this is coming. If it's not in a state where you live yet, it will be soon. EPA has said, states, if you don't do the job, we will impose limits on you, so get the job done. Now, there are already state and regional standards on nutrients in a lot of areas. It's very dependent on the quantity and quality of the waters that the waste is going to. For example, if your sewage treatment plant is emptying into the ocean, typically you don't have to worry about nutrients. There's plenty of dilution, and it's not going to cause any measurable effect. However, there are some waters like the Chesapeake Bay or the Gulf of Mexico, the Mississippi River, where nutrients play a role in the ecosystem and can have negative effects. But usually right now we're seeing standards being very tight when a treatment plant is emptying into a sensitive stream, a fishing stream, a small shallow lake, and so on, where eutrophication can occur very easily. We're seeing ammonia limits down to as low as 0.2 to 10 milligrams per liter, and total nitrogen limits down between 5 and 10 milligrams per liter, and phosphorus limits as low as 0.05 to 2 milligrams per liter. Very low limits on phosphorus. So let's talk about how to remove these nutrients from wastewater. Now we'll talk about nitrogen removal first, and then we will discuss phosphorus removal. As I mentioned before, there are three major types of nitrogen in wastewater. There's the organic nitrogen, which mostly comes from urea, a chemical in urine. There are the ammonia forms, and that's just the ionized and unionized forms of ammonia in water. And then there's nitrite and nitrate, which are mostly formed during the treatment process. We can classify these different ways. We have total inorganic nitrogen, which is the ammonia forms and the nitrate and nitrite. We have what we call total Kjeldahl nitrogen, named after Johan Kjeldahl, a wastewater scientist. And that is the organic nitrogen and the ammonia forms. The reason he categorized those separately is because those are the two forms that actually come into a treatment plant that we need to deal with. And so using TKN, or total Kjeldahl nitrogen, is a measure of the amount of nitrogen coming into the treatment plant that the processes need to handle. Finally, we have total nitrogen, which are just the sum of all the forms together. Now, if we just look at the TKN, which is the part that's coming into the waste treatment plant, typical is about 40 milligrams per liter coming into the treatment plant. Of that, about 3/4 of it is ammonia, and about 1/4 of it is the organic nitrogen. Ammonia forms are pretty easy to get rid of. We can take those down to non-detectable levels quite easily. The organic nitrogen is a little more difficult. Of that, about half of it, or almost 5 milligrams per liter, is readily biodegradable. It can be done fairly easily, not too much of a struggle. Another part of it is kind of particulate in nature and not dissolved, and it's a little more recalcitrant. It's harder for microorganisms to break it down. And finally, there's also an actual dissolved portion that's recalcitrant dissolved organic nitrogen, about 1 milligram per liter. So we can easily get the total nitrogen down to about 5 milligrams per liter. Getting below that takes some fairly complex processes. There are chemical methods for removing nitrogen. We can use air stripping to strip the ammonia out of the water, but ammonia doesn't smell good, and so if you release it into the atmosphere, the neighbors are going to complain. You can use chlorination, which will break down organic material into smaller components. But if you mix chlorine with some of these organic materials, you get chlorinated hydrocarbons, which are cancer-causing chemicals. So that's not a great idea either. You can use ion exchange, which is mostly used to remove nitrate. It's often used in drinking water to remove nitrate from drinking water, but it's expensive because the media has to be regenerated and there's a significant power cost. Luckily, nitrogen is not difficult to remove biologically. And this is the way the vast majority of wastewater treatment plants remove the nitrogen from the wastewater. If you attended our activated sludge session, we talked a lot about BOD removal. During BOD removal, the nitrogen in the organic matter is converted to ammonia. This is the first step in any nitrogen removal process. The second step is called nitrification, and this is to remove ammonia. It transforms ammonia to nitrate. And then there's a final step. If a plant needs to get rid of the nitrate as well, there's a step called denitrification. That is not the inverse of nitrification. That is, we're not going back from nitrate to ammonia, which wouldn't help us. Confusingly, but luckily, it's not the same thing. We're converting nitrate to nitrogen gas, which is then released into the atmosphere, which is 80% nitrogen anyway. So these are the steps that a treatment plant can be designed to go through to completely eliminate or grossly eliminate the nitrogen coming in. Let's talk about each one of these in series. In the BOD removal stage, remember this is where the organic nitrogen gets converted to ammonia. And this stage is the main treatment stage in all wastewater treatment plants, where we're trying to break down the biochemical oxygen demand in the treatment plant. And this is a natural part of this process. The microorganisms convert the organic material to carbon dioxide, water, and ammonia. This is an aerobic process. That means that oxygen is required. These microorganisms that do this need oxygen to survive, and it's part of their growth process. And so we can do this in two ways. We can do this in an activated sludge process, or a suspended growth process, we call it. We can also do it in some other types of biological processes, which are widely used, but not as much as activated sludge, called fixed film processes, where the bacteria is encouraged to grow on some kind of a media or substrate, and the water is trickled over it or passed through the media, and the microorganisms don't swim freely in the water. They're fixed on this media. But you can use that for BOD removal. Trickling filter and RBC are typical examples of the kind of equipment that's used to do that. Now the next step, nitrification, is when we want to eliminate the ammonia. And we're converting that ammonia to nitrate. This is the major method for ammonia removal that's used in wastewater treatment. In this stage, microorganisms convert the ammonia to nitrite, NO2, and then to nitrate, NO3. And there are actually different organisms involved in each of these steps. But the organisms that convert the nitrite to the nitrate do it very quickly compared to the others, so there's almost never very much nitrite in a system. It's essentially going from ammonia to nitrate with very little intermediate step. Chemically, it's there, but it happens so fast that there's typically very little of it in the process. This also is an aerobic process. That means the microorganisms that do this job also need air to live. And so we can do this in an activated sludge system. We can do it in a fixed film type system like a trickling filter or an RBC. But there's some differences here between the nitrification step and the microorganisms that accomplish that and the ones that accomplish BOD removal. Now, all living organisms need carbon for growth. Animals eat plants and other animals to ingest their carbon. Plants pull carbon dioxide out of the atmosphere through photosynthesis for their growth. Microorganisms are the same way. Heterotrophic bacteria use organic compounds as their carbon source. Like animals, they ingest it. It's not the same kind of ingestion that you or I eating it, but essentially that's what they do. They take these organic compounds that have carbon in them and modify them in their cells and use that carbon to reproduce. These organisms are the ones that break down the BOD in the main treatment step of a treatment plant. They're fast growing. That is, they have a reproductive cycle that is as quick as 1 to 2 days. There is another kind of bacteria, however, called autotrophic bacteria that use carbon dioxide as their carbon source. The organisms that accomplish nitrification are these autotrophic organisms. So they're different from the ones that break down the BOD and produce the ammonia. And they're slower growing, like plants are slower growing than animals. You can make the analogy. Plus, they're more sensitive to pH and temperature. In low temperatures, they're not very active. In high temperatures, they're much more active. So to design a nitrification system, we have to be aware of these parameters. So to achieve good nitrification, we must have first good BOD removal, because the heterotrophic organisms will always outcompete the autotrophs. So if you don't first remove all the BOD, you won't have very many of these nitrifying organisms because they will be outcompeted. You also need a longer solids retention time than in a conventional activated sludge system, because you have these longer lived organisms, or actually a longer life cycle organisms, reproductive cycle, and so you have to have your solids in the system for a longer time than you would just to remove BOD. If you want to nitrify, you have to have a longer sludge retention time, solids retention time, so that we don't wash out these nitrifying organisms from the system. So here's a typical plant. We have an aeration basin for BOD removal. It's being aerated. If a plant then wants to nitrify, that is, get rid of ammonia, they can simply add another basin and also aerate it. And of course, you have to size these properly, and there are equations and math for doing that, which is a whole college course. But essentially, you're just adding additional aeration capacity to be able to accomplish ammonia removal or nitrification. Now, obviously, you can do it in a single basin as well. If you're designing a new plant for both BOD removal and nitrification, you just build one bigger tank, and that'll accomplish it. Here's an example of a combined stage BOD removal and nitrification system. Most oxidation ditches, like I talked about in the activated sludge class, are designed for both BOD removal and nitrification. And they will remove the organic material as measured by BOD, and they'll remove the ammonia. You can also do this. I talked about fixed film processes. This is a trickling filter where the wastewater is trickled over a media. It's an open media, so there's lots of air that can pass through the media, and microorganisms grow on that media. In the upper part of the filter, They're feeding on the organic material and removing that BOD. In the lower part of the filter, you get the nitrifiers growing, and they remove the ammonia. And you can actually tell the difference. If you pull a column of the media out of the trickling filter, they're different colors in the top and the bottom because those microorganisms actually are different colored. The last stage in ammonia removal we call denitrification. And remember, this is the conversion of nitrate, or the fertilizer form of nitrogen, into nitrogen gas, which is then just released to the atmosphere. This is the major method for removing nitrate in wastewater, and it's accomplished by heterotrophic bacteria. That is, bacteria that use organic carbon as their food source, but it's an anoxic process. That is, there is no dissolved oxygen. There are some microorganisms that when there is no oxygen present, they can break the nitrate molecule and use the oxygen as their oxygen source, thus releasing the nitrogen into the water and into the atmosphere. And we can do this in an activated sludge process, although we don't add air. Or we can do it in a fixed film process, but again, there can't be air, so it can't be an aerobic process like a trickling filter. Again, we can do this in two stages. Here we have on the left our BOD and ammonia removal. So we've converted all of the nitrogen at this point to nitrate. That nitrate then goes into a second stage that we mix, but we do not put air in it. And the nitrate is then converted to nitrogen gas. Now remember, I said that these organisms that accomplish this are heterotrophic. That is, they need a carbon source. They need organic carbon. Well, if you look at this, there's a problem. In the first tank, we've removed the BOD. That is, we've broken down virtually all of the organic carbon, and it's already been used up by the organisms in that basin. So there's very little organic carbon left to go into the denitrification stage. So in this kind of a flow sheet, we often have to add some additional carbon. It's usually done in the form of methanol or acetate, but it's an ongoing chemical cost, which most plants don't like. But it works very well. This is some denitrification filters that are used. This is actually a fixed film type of a process, using sand grains in those tanks as the media to support the bacterial growth. But you can see there's no oxygen being put in there, and the water flows up through the sand in this anoxic environment, and the microorganisms break that nitrate down into nitrogen gas. Somebody had the bright idea, rather than add carbon at the end, why don't we figure out a way to put the denitrification step at the beginning, where we have plenty of organic carbon coming in our feed. The way this system works, we have our feed and our recycle from the clarifier coming in to this zone. This is an anoxic zone. There's no air added. So we don't get rid of much of the BOD or the ammonia. We're worried about nitrate at this point. So that BOD and ammonia goes into our aeration stage, where we add the air, convert the BOD and ammonia to nitrate. Well, now we have nitrate at the back end, whereas our nitrate removal step is at the front end. So we add a pump, and we recycle nitrate into the front zone, where it has plenty of carbon. Now it has nitrate, but no oxygen, so these organisms can break down the nitrate, use it as their oxygen source, and release nitrogen to the atmosphere. This pump actually recycles a large amount of wastewater. If the flow coming in, the feed, is Q, the recycle can be as much as 4 to 5 Q even to get good nitrate removal. Again, we do mix this zone, although we don't add air, and we produce nitrogen. I really like Paul's animations here. This process can reduce the total nitrogen down to levels about 5 to 10 milligrams per liter. Remember, there was 40 coming in, so we removed it down to as low as 5. So we've taken out 7/8 of the nitrogen with this process right here. And it's a simple addition to a regular activated sludge process. All you do is put the tank on the front end and add a recycle pump and a mixer. This is a picture of one of those processes. You can see in the back of the basin, there's no air being added. You can see it's just, there's no bubbles on the surface. That's the anoxic zone. And then it moves into the aeration zone as it comes towards us in the picture. Now, somebody said, we can do better. And so in 1971, we have what's called a BOD process, named after James Bernard, who is a wastewater scientist still active in the field. And he said, well, let's take our MLE process that we just described and add on the back end a couple of additional zones. So this is our MLE process, which we just talked about, functioning. But you realize that there's still some nitrate left in the wastewater at the back end of the aerobic zone. That's what's being pumped into the anoxic zone. So there's obviously still some nitrate in the system. Dr. Barnard said, let's add some post-anoxic volume so that we can, again, convert that nitrate that's left into nitrogen gas. And that process actually produces a little bit of ammonia and BOD that then we eat up in a final aerobic stage. It's quite small, but it's just enough to get rid of the residual that's created by the microorganisms in the anoxic stage. This process, although there's more tankage, it does a better job. We can get down to levels as low as 3 to 4 milligrams per liter. Westech has plants designed and running that are consistently producing less than 3 milligrams per liter of total nitrogen using this type of a flow sheet. So it's very effective. This is an example of a four-stage BOD process. You can see there's more tankage and more mixing, so there's a little more maintenance to be involved in the treatment process, but it does a very good job of removing nitrogen. We've now finished talking about the nitrogen removal process. In the next session, we will go on and talk about phosphorus removal and then a short summary of both.